Sir, is the presentation visible?
Yes, please.
Yeah, thank you. This is basically our research on investigation of self-organized criticality in daily cases of COVID-19 in India and in states. We are focusing basically at first in India, and afterwards we will be moving outwards also. So here is the abstract. The research area is kind of in a computational and statistical biology. But what we are trying to do is include more of pathology and other things in the other factors in the thing, so that we are more connected to various natural processes. Because modeling is something very different from analyzing results from actual natural processes. And our objectives are actually finding out how the processes are going on, and then afterwards using that to enhance our models or enhance our systems by which we are predicting certain kinds of epidemic or other ecological phenomena. So as we all know, COVID-19 is a huge event, huge pandemic that has been going on all around. India has faced a second wave and faced very bad consequences after that. So we think that it is a very active area of research, and it needs our concern. So basically, the idea of SoC is, if a dynamical system exhibits SoC properties, it will resist itself to perturbations from external forces. So that is the basic idea of SoC. And if we see if dynamical spread models actually contain SoC properties in them. The basics of fractal mathematics comes here. We all know Mandelbrot. He was the father of fractal geometry, of fractal mathematics, as we can say now. He envisioned lots of phenomena that in nature are peculiar, because they do not follow the normal classical geometry, and they have certain peculiar properties in them. We may consider some things which are repetitive in nature or self-similar in nature, those are fractals. Here are the few properties of fractals that were given by Falconer. They possess fine structure and no characteristic lengths, because they have infinite lengths, as we may see, because changing scales we may change their lengths as well, and they are highly irregular. One important point is the fractal dimension is always greater than their topological dimension, and they often show unusual statistical properties. These are the few important points which I wanted to highlight in this slide. So then Higuchi was a mathematician who developed a exponent called Higuchi fractal dimension for one-dimensional time series. And so it's a very easy algorithm. I will show in the next slide that it's a very easy algorithm for seeing if a time series data contains fractality in them. Here is the idea of self-organized criticality. So in large dynamical systems, systems have property to lose some energy or to gain some energy in order to stabilize themselves. So that is the basic idea of self-organized criticality for a dynamical system. And for systems like epidemic spread models, self-organized criticality is a very dangerous situation, might be a very dangerous situation. We actually don't very particularly know, because some very non-fatal diseases might show self-organized criticality, but they will not cause any real problem to human population. So we need to study a lot in depth about the process. So the idea of self-organized criticality was proposed by Bach et al. And they were for open and extended driven systems, like showing avalanche energy distributions. We might find an example of sand pile. This is a very common example, sand pile model. Sand pile models are actually self-organized critical behavior property showing model. Also, forest fires and things like that tended to show self-organizing critical properties. Here is our new method of calculating the moving average for smoothing the data. So generally, we actually compute moving average by other means, but here we considered, since the data points are not very large, we have considered a dynamic moving average, so that we do not distort the data. we have conserved the data for even x equals to 1 and x equals to the last and the first points also. Here is the algorithm for the fractal dimension by Higuchi's algorithm. It's a fairly trivial mechanism. We just need to compute another time series from the original time series, and then we measure the lengths, peculiar lengths, and then we do just general regression to find if at all, if the thing shows a fractal nature. And in this regard, I may say that scaling analysis has to be performed before this. This is the idea of actually the mathematics of self-organized criticality. In systems which behave in such cumulative distributional properties, we use this algorithm. It's a very easy algorithm, and it can even be done by MS Excel. It's very easy to compute. So we take this approach for calculating if at all a dynamical system, for example, a one-dimensional time series data shows properties of self-organized criticality in itself. The mandatory aspect is that the presence of self-organized criticality can be established if the value of zeta approximates the right-hand limit of 1. So we consider the values in between 1 to 1.1, like that. Here is our data. So we have taken the first wave, and we are actually also working on the second wave, because our first wave results did not convert to any conclusion if second wave will arrive or not. Here are our previous results from the previous analysis we did for some major affected states. Almost all states showed fractal natures in them, but none of them actually showed critical nature, self-organized criticality in them. But we see that all of the states have faced newer waves after that. So here comes the conclusion and some newer results. This is the data we taken from 2nd March to the almost the end of the first wave, and we can see that the fractal dimension is greater than 1. Means it's greater than 1, so it contains fractal nature, monofractal nature in them, and the SoC exponent is 1.394. So we still see that there was no evidence of self-organized criticality in the mechanism, but a second wave came. So we think that there is room for, yes sir, I'll conclude. There is more room for actually working in the area, so that we can conclude our results by looking at what serology suggests, or what actually the results suggest, and we analyze them to get better results or better prediction about the future. Here are the challenges ahead and ongoing research. So these are the main points which we are focusing on now. One is analyzing the predictability of new waves by analyzing fractal and SoC profile. Secondly, analyzing the change of SoC profile in different waves of a pandemic. So we see how SoC profile changes with different waves or different spread dynamic changes. Third is understanding how nonlinearity and chaos adds up with SoC and gives us insight on the governing dynamics. Hence, we can have better modeling for the future predictions like that. Then is the state-wise analysis of cases and further global analysis that may help us understand deeper of dynamic spread modeling. So this is one important point which we want to focus on later. And last is formulating dynamic modeling, considering the results of SoC profile, fractal analysis, and as I've said, nonlinearity and chaos, and their relation to the spread of the pandemic. These are the main challenges we are working on, and main things we are thinking to implement, because this is a very new field to study and very broad field in connection of mathematics to real world pathology or real world serological data or like that. This is our team. We are basically from University Institute of Technology, the University of Burdwan. I am Dibakar Das. Then I have my team members, and our advisor is Dr. Kaushik Ghosh, and I am actually specialized in epidemiology from Johns Hopkins University via Coursera. Thank you, and please stay safe in the pandemic. Thank you, sir.
Thank you so much, Dibakar Das. Sir, if you have any queries, please feel free to ask. Dear panel member, if you have any questions, please feel free to ask.
So, why you are calling it self-organized? In what sense you have claiming that it is self-organized? Can you please elaborate a bit?
Yes, sir. So basically, we have shown that this is not yet self-organized. So if a dynamic epidemic model is actually self-organized, if we introduce measures like for per se vaccines or certain things like con- uh, contract tracing or contact tracing and isolation, so there are high chances that measures will fail if a model is exhibiting SoC. Since we have seen that it is not yet showing SoC, we are actually happy and we are actually feeling positive about the fact that we may control COVID-19. But here comes one problem that we have faced, that the profile of SoC has given us no insight into the coming of newer waves. So we are actually trying to see how we can find some correlation between the SoC model, means the output of the SoC model, and the serological calculations that are going on outside.
So, so you are thinking that you can work with by developing this self-organized model, and but in that cases, I'm suspecting some challenges. So, have you
Yes.
thought about some challenges or issues that you have to face and you have to overcome to develop this model?
Yes, sir. Actually, the most important problem with the SoC calculation or certain computation which takes the algorithm of SoC is that requires a huge sample size or the data size to be huge. We can see in this slide, yes, uh, we can see here that here we have done a generalization of the formula. So actually, for very small data sets, it's a bit tough to actually give proper results. First is that, and second is we need a very huge, deeper study uh, to see if there is some very proper correlation between our SoC given SoC value and the real world serological data or the real world consequences, like if the new waves are coming, if the how the population is affected by a new variant. We actually need to study deeply on that. That are the most important challenges, right?
So Dibakar, thank you. It's quite nice work, and so carry on.
Thank you, sir.
We have some distinguished researchers as well in the audience panel. So if anyone is interested, they can also have some questions or comments and suggestions.
Okay, sir. From the audience panel, if you have any suggestion or queries, please feel free to ask to Dibakar Dash. Okay, I guess no questions. So if there is no questions, so we will to move to the next
Sir,
presenter.
can I just include a concluding note at the end? There are some futures to the work. So we may work with like things of AI in the field and introduce how means pre-planned experiments where simulations are done. So we have a broad spectrum of work left in the field, because this is a very new field which we are advancing on. Thank you, sir.
Okay, thank you.